Come on. Okay. Let's see. So this will be so. So as I said before I started recording, this is the last portion of the introductory part of the eigenvalue problem about its properties and things to be concerned about in algorithm development, and then the first simplest algorithm for producing one eigenvalue and eigenvector, and paving a way towards an algorithm that can find at least all the eigenvalues, or at least the entire Shor decomposition. Okay, so first, look at the perturbation theory. And to draw a parallel with the problem we spent so much time on of AX equals B. Now, AX equals B, we had to worry about conditioning. We compute the condition number of a matrix, and that gives us an idea of how sensitive the AX equals B problem is to perturbations in the problem. Like if A or B were to change by a little bit, would that lead to a large change in the solution? And the answer is yes, that can happen if A is ill-conditioned. So what about if we're solving the eigenvalue problem and the matrix A changes? Under what circumstances are the eigenvalues or eigenvectors particularly sensitive to such perturbations? Okay. So the first result about related to sensitivity is a theorem called the Gershkorn circle theorem or the Gershkorn disk theorem. And so what this theorem says is if you were to draw disks in a complex plane that were centered at the diagonal entries of A, and then the radius of a disk would be equal to the sum of the absolute values of all the other elements in that diagonal entries row. So we're focusing on row I. So each row of A gets a disk. A diagonal entry of that row is the center. Some of the absolute values of all the other entries in that row is a radius. And what this theorem says is that if you consider the union of all of these disks, which can certainly overlap, the eigenvalues have to fall within those disks. So what could be interesting is suppose A is close to a diagonal matrix, like maybe the off-diagonal entries make very little contribution. That means that the radii of these disks would be very small, small enough to be disjoint. Then from those disks, that would indicate that the diagonal entries of A would be excellent approximations of the eigenvalues. Okay. Now, this theorem is actually not difficult to prove. It is actually one of the explorations in this section. I don't believe I assigned it. And it comes from considering the matrix vector product, A times X equals lambda times X, and break it down to the diagonal term and off-diagonal terms to show that this inequality has to hold. Okay, but to give an example of the Gershkorn theorem. So here's a matrix, and these are the true eigenvalues. And then the Gershkorn disks come from taking the diagonal entries of A and making those the centers of the disks. And then for each row, like for this row, we add up the absolute values of the off-diagonal entries, and that gives us a radius. So 4 for the third row, 3 for the second row, and then 2 for a first row. And so what we see is like this eigenvalue is close to, pretty close to 7. It falls within this disk. This eigenvalue is not too far away from 2. It falls within this disk. And then this one, close to -5, falls within this one. Now, one thing I want to point out, though, about the theorem, because this is a natural misinterpretation of it. So you have n eigenvalues, including repeated ones, and you have n disks. It does not mean each disk contains an eigenvalue. So if you look at the wording of a theorem states that all the eigenvalues lie within the union of the disks. So there's not this one-to-one correspondence. Okay. Actually, this is an interesting exercise to see like what the disk looks like as you start with a diagonal matrix and then you perturb the matrix to include off-diagonal entries. For example, you could define what's called a homotopy, a function on the interval 0 to 1, where at 0 you have just a diagonal, and then at 1 you have the entire matrix, and see how the Gershkorn disks change as a function of that homotopy. Okay. Now, with the AX equals B problem, we have a straightforward measure of sensitivity. That's the condition number of a matrix. We'd like to have the same kind of thing for the eigenvalue problem, if we can. Okay. Okay. I'm gonna make a subsection here. Okay. Now. Okay. So let's suppose that lambda is a simple eigenvalue of A. Now, as a reminder, what that means is that is an eigenvalue of multiplicity 1. So it's only a simple root of a characteristic polynomial, which is where the term simple eigenvalue comes from. So it only has one linearly independent eigenvector. Well, actually, yeah, just one eigenvector, period, or any multiple thereof. So we'll call the eigenvector x, and then the left eigenvector, we'll call that y. Because repeated eigenvalues will be a different story, and I'll get to that later. So what that means is this matrix, A minus lambda identity, is known to be a singular matrix when lambda is an eigenvalue. But we could say something more here. The rank is n minus 1. In other words, the null space of this matrix has dimension only 1. The null space is a span of this eigenvector. Now, y is a left eigenvector. That means it's also an eigenvector, or like a regular eigenvector, of a Hermitian transpose, and the eigenvalue is the conjugate. So y is orthogonal to the range of A minus lambda I. So in general, we can say is the orthogonal complement of a range of a matrix is equal to the null space of the transpose or Hermitian transpose if it's complex. So I'll go ahead and write that down here. So if I take range of A minus lambda identity, and then I take its orthogonal complement instead of all vectors that are orthogonal to vectors in here, that would be the null space of the Hermitian transpose, but that's the null space of A Hermitian transpose, which should be uppercase H, minus Hermitian transpose of this, but that's just the conjugate of lambda. So a vector that is orthogonal to everything in here must be in the null space of here, but y is in this null space. So in this example, that's the span of y. So y being an eigenvector of this matrix with this eigenvalue is in a null space of this matrix. Therefore, it is orthogonal to the range of A minus lambda identity. So what that means is, the reason why I'm going through all that is, if y is orthogonal to this whole space, which has dimension n minus 1, this range, it cannot also be orthogonal to x. So, because x defines a null space of A minus lambda identity. So if y is orthogonal to both this space and this space, it must be orthogonal to all of Cn. But the only way that can happen, because y itself is in Cn, it's an n-dimensional vector, it would have to be 0. But y cannot be 0 because y is a left eigenvector. That alone means it's non-zero. So the main point to make here is y and x cannot be orthogonal to one another. So that means that their inner product is non-zero. So what I can do is normalize x and y so that the inner product is actually equal to 1. So we're just going to make that assumption. Okay, so now that we have that, so now we're going to let a and x depend on a parameter epsilon. So when epsilon is 0, we just have ax equals lambda x. And a of epsilon is defined this way, that we're perturbing a by some matrix f, and we assume that f is a matrix of norm 1. So epsilon really indicates the size of this perturbation of a. So then what I could do to study sensitivity relates very closely to derivatives. Oh, what's a funny word?
Homotopy. I don't know why it sounds so funny.
Oh, well, yeah, I get it.
I don't know.
Okay. All right. So if I take the derivative of this equation with respect to epsilon, that would require the product rule, and then I evaluate at epsilon equals 0. So a derivative of a of epsilon would just be f, and then I have x of 0, which is just x. And then for the other part of the product rule, I have a times x prime, which is unknown at this point. And then I take a derivative of the right side that also requires a product rule. So I end up having a derivatives of the eigenvalues and the eigenvectors, which is good because that helps you understand their sensitivity. So now I take the inner product of both sides of this equation with y, and then simplify as much as I can. And y Hermitian transpose x, that is 1. Whoops. And y Hermitian transpose a, y is a left eigenvector. So that's the same as lambda times y Hermitian transpose. So I take that into account here. And as I mentioned before, this is 1. So now we have this. So now, what do I get from that? Because I want lambda prime. Now, the thing is, notice here, these terms cancel out. So I have lambda prime is equal to this. So now take absolute values and use this Cauchy-Schwarz inequality, which says that, okay, so really what I can say is Cauchy-Schwarz inequality would give me the norm of y, times the 2 norm of f times x. Okay, so Cauchy-Schwarz inequality brings me to this. Oh, there's a LaTeX error somewhere. Okay. Okay. Oh, it went away. Now these are properties of norms. Norm of fx is less or equal to norm of f times norm of x. But norm of f is 1. So now I have this. Now, no, I do not want to ask Siri anything. Now, the angle between x and y is given by this. It's the inner product divided by the norms. Well, the inner product is assumed to be 1, so now I have this. So in other words, the derivative of the eigenvalue is less or equal to 1 over cosine of the angle. Okay. So this quantity, 1 over cosine, that's defined to be the condition number of this simple eigenvalue. So how do we interpret it? Suppose now x and y cannot be orthogonal, but suppose they are nearly orthogonal. That means that this angle theta is nearly pi over 2. That means that cosine of theta is nearly 0. Therefore, the condition number is large. So just as ax equals b is ill-conditioned if a condition number of a is large, if this quantity is large, then the eigenvalue is ill-conditioned. So in other words, a small change in a can lead to a large change in this eigenvalue. But it only applies for simple eigenvalues, because if you have a repeated eigenvalue, you could have multiple left and right eigenvectors, and so the angle between them is not well defined. You can have many different angles. Right. So what we can say is, more precisely, if you have an order epsilon perturbation in A, then that causes an order epsilon over cosine theta perturbation in the eigenvalue. So it's still order epsilon, but it could be a large constant times epsilon if this angle is nearly 90 degrees or pi over 2. So another thing we can obtain from its condition number, if it's large, then A is close to a matrix of a multiple eigenvalue. And as you see before, repeated eigenvalues can certainly be a problem. Okay. So as an example, all right, so for this matrix, here's an eigenvalue that's fairly close to 2, and there's a left eigenvector, a right eigenvector. So even though this vector is pretty large, if you actually take the inner product of these two, you get 1. So we're normalized to make that happen. So the condition number turns out to be somewhat large, not really large, but this is not really the best conditioned eigenvalue based on the angle between these two vectors. So it turns out that a pretty small perturbation of this matrix, to give this one, you can look at the entries and see they're fairly close together, has a repeated eigenvalue of 2. But we can also say that a relatively small change to this matrix can lead to a relatively large change in this eigenvalue. All right, so that's for simple eigenvalues. What can we say about repeated eigenvalues? Okay. Now, as I mentioned last time, the eigenvalues of a matrix are continuous functions of the entries. That does not mean, though, that they are differentiable functions of those entries. So as an example, if we have this matrix here, and we assume that A is positive, well, if epsilon is 0, this is actually a matrix that has a repeated eigenvalue. So if I take a characteristic polynomial and I get this, then I go ahead and take a roots by quadratic formula, and I get the eigenvalues that are perturbations of 1. But notice it's epsilon to the perturbation is order epsilon to the 1/2. So if I take the derivatives of these eigenvalues with respect to epsilon, then we see that the eigenvalues are not differentiable when epsilon equals 0, because the derivative is goes infinite. But what we see from here is, again, it's a lower order of epsilon. And remember, for something that's small like epsilon, it's a small number. You take power of it less than 1, it increases. So in general, if an eigenvalue is repeated and is associated with a p by p Jordan block, then if you change A by order epsilon, you change the eigenvalue by epsilon to the 1 over p. So a larger change in terms of orders of magnitude compared to the case of a simple eigenvalue where p would just be 1. So the more defective the eigenvalue is, the more sensitive it is to changes in the matrix. All right. So that's sensitivity of eigenvalues. What about sensitivity eigenvectors? And this part I may need to not really fully cover. And I'll include it in the notes, certainly. What we really do is we don't study sensitivity of eigenvectors necessarily, but invariant subspaces that can have any dimension. So an eigenvalue will cover eigenvectors since if you take a span of an eigenvector, that is an invariant subspace of dimension 1. Okay, and so a key result that we have here is that if you make an order epsilon perturbation in A, that leads to this kind of perturbation, epsilon over this quantity perturbation in the invariant subspace, that so here we have a situation where A has this kind of Schur decomposition, where if matrix Q is orthogonal and it has you break your columns down by this, T is upper triangular, and so we consider these two diagonal blocks. So the question is, how separated are these matrices, T11 and T12, and that's defined by this measure here. So the less they are separated, the more sensitive this invariant subspace Q1 is to perturbations in A. And a specialization of this to a one-dimensional invariant subspace, in other words, an eigenvector. So let's suppose that here we have this breakdown, and it's assumed that Q1 has R columns and T11 is R by R. But let's assume R equals 1. That means Q1 is actually a single vector, an eigenvector, and T11 is R by R matrix. It's just a number if R equals 1, and that would be the corresponding eigenvalue. So what happens in this case is, how separated is the eigenvalue from this matrix T22? And in that case, the formula for separation can be simplified. It turns out to be the smallest singular value of T22 minus lambda identity. So in other words, if lambda is close to any of the eigenvalues from T22, then this smallest singular value will be small, near 0. So the separation will be small. But that makes the eigenvector more sensitive to perturbations. So the main point, really the only point I want to make from this discussion, which I know I'm glossing over, is this. If an eigenvector has an eigenvalue that is clustered near other eigenvalues, then those eigenvectors are more sensitive. So to summarize the whole discussion of sensitivity of eigenvalues and eigenvectors, here are the key points. So first of all, there's no clear relationship between how sensitive an eigenvalue is and how sensitive its variant subspace or its eigenvector is. You can have one being sensitive, the other being insensitive. So as some examples, well, first of all, before we talk about that, what actually drives sensitivity of eigenvalues and eigenvectors? That is summarized right here. The sensitivity of an eigenvalue depends on the angle between its left and right eigenvectors. Are they nearly parallel, in which case they're insensitive, or are they nearly orthogonal, in which case it's sensitive? The sensitivity of an eigenvector depends on how clustered the eigenvalues are. Another way to put it is, I remember a description from Golub and Van Loan, which is a numerical linear algebra textbook I used, naturally because my advisor co-wrote it, that eigenvectors corresponding to nearby eigenvalues are, quote, wobbly. So let's suppose we have a particularly sensitive eigenvalue. So its left and right eigenvectors are nearly orthogonal. But if that eigenvalue is far away from other eigenvalues, the eigenvector that goes with it can be insensitive. On the other hand, if the eigenvalue is well conditioned, so it's insensitive to perturbations, if it is very close to other eigenvalues, then its eigenvector can be ill conditioned. So you just never know. Okay, so now, so any questions up to this point? This concludes the discussion of the sensitivity part. Right, now let's finally get into algorithms. Oh, definitely starting this on a new page. Okay. Okay, so what can we do to actually find eigenvalues now that we know something about the problem? Like, we know we'd like to reduce the matrix to triangular form to get the Schur decomposition, but we don't yet know exactly how we can do that. But it turns out what we can do to solve that problem can be figured out by focusing on a simpler problem. And instead of trying to find all the eigenvalues and eigenvectors at once, which is our ultimate goal, what if we just try to find one eigenvalue and its eigenvector? Because we've already seen that if you are able to obtain one eigenvalue in its eigenvector, you can use deflation and start towards making a matrix upper triangular. So that helps. So let's try to find one eigenpair. And from now on, I've been talking about cases where A can be real or complex, but just to simplify things, we're going to assume that A is real. So the first method we'll see is called the power method. All right, so we'll assume that these are the eigenvalues of A. Now, even though A is real, these eigenvalues can still be complex. And we'll assume that the first one, the largest one, is strictly greater in magnitude than all the rest. So magnitudes might be equal after that, but this one is strictly larger. And I'm also going to assume that A is diagonalizable. Now, that's not necessarily true, but just to simplify the discussion. So here are n linearly independent eigenvectors, and that have these corresponding eigenvalues. So not really a requirement for a method, but to help understand why it works, it helps. Okay. So let's suppose I have an initial guess of an eigenvector, x0. So what I do is I just take this initial guess and I keep multiplying by A nonstop. So that gives me a sequence of vectors. Each vector is just A times the last one. So in other words, xk would be A to the k power times x naught. So the reason why I assume A is diagonalizable, it allows me to write x naught as a linear combination of the eigenvectors. And what that allows me to do is come up with an expression for xk in terms of these coefficients. So xk is a to the k x naught. But if I apply a to the k to this, that means I'm applying a to the k to each eigenvector. So that would give me each eigenvalue raised to the kth power times its corresponding eigenvector. So because these are eigenvectors, this becomes this. So now what I'll do is I'm going to write the first term of this separately. Then we'll have a sum from 2 to n. And I'm also going to factor out x1 to the kth power. So then I have to divide by x1 of k power. But we know that lambda 1 is the largest eigenvalue. It's also non-zero, so dividing by it's fine. Okay. So now, what happens to this expression as k goes to infinity? Well, what happens is this whole thing, that is a coefficient of xi within x sup k. So as k goes to infinity, these coefficients of the other eigenvectors are going to 0. So as I keep multiplying by a, the direction of this vector converges to that of x1, because what we'll end up with is this part's going to go away eventually, or converge to completely going away. And so what's left is a scalar multiple of x1. So in other words, under the assumptions that I have, this vector xk, as k goes to infinity, will converge to an eigenvector. It will converge to x1, or at least a multiple of it. So now I have an approach to finding one eigenvalue and eigenvector, of an eigenvector corresponding to the largest eigenvalue. So this is called the power method, and there's very little to it. Just a few lines. We choose the initial guess. We assume it's a unit vector. So then I multiply by a, and then I normalize it, because if the largest eigenvalue of a is greater than 1 in magnitude, the size of its vector will go to infinity. Whereas if the largest eigenvalue of a is less than 1 in magnitude, then this vector will go to 0. So that's why I just go ahead and normalize it, because I really only care about the direction of its vector anyway. So these vectors, q0, q1, q2, etc., are all unit vectors. And this sequence of unit vectors, under this assumption, will converge to the eigenvector for the largest eigenvalue of a. Okay, so we can keep going until qk converges. So if it converges, and that is a big if, the power method does not always succeed. But if it does succeed, we'll get a multiple of x1. And I could use that to get the largest eigenvalue, lambda 1. But here's the problem. The rate of convergence is lambda 1 over lambda 2. So in other words, the distance between qk and x1, the subspaces, decreases by roughly this factor. So what if, now lambda 1 is, well, actually, that should be, okay, yeah, decrease by this factor. So in other words, be multiplying by lambda 2 over lambda 1. Okay. So, but the problem is, what if lambda 2 is only slightly smaller in magnitude than lambda 1? But that means that this distance is going to decrease very slowly. And this takes us to the drawback of a power method. So if lambda 2 is almost as large, it'll converge slowly. If the second eigenvalue is equal in magnitude, but not the same, like if they have opposite signs or complex conjugates, the power method will actually fail to converge. Because what will happen is, up here you'll have a term from this sum that won't go away as k goes to infinity. So instead you'd have a linear combination of like x1 and x2. It still gives you something, but it doesn't give you what you're after. Like you might get something in a higher dimensional invariant subspace. Now, one thing I've come across when I've actually implemented the power method in Matlab is what if it does converge, but this eigenvalue is negative? If you do a straightforward convergence check, like, is the difference between qk and qk minus 1 going to 0? Well, the problem is, if the eigenvalue is negative, then qk will keep negating from one iteration to the next. So you have to be mindful of those things. And in terms of your implementation. So what I did in that case, there's more than one thing you can do, is what I would do is normalize it in some way to not be affected by multiplying by a negative number. Like if I make sure that the first component is positive, then I could check for convergence in the usual way. So these little details like that can make or break mathematical software, but they have to be taken into account, that aren't necessarily explained in books. But this one is in my book. No. Okay. 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 So let's suppose you try the power method out and it does converge. So now you have x1. You know that's the eigenvector that goes with the largest eigenvalue. How do you get the eigenvalue? You use this expression. It's called a Rayleigh quotient. So you just go ahead and compute this. where x1 is the eigenvector you converge to, because if x1 is an eigenvector, then you would just get lambda x1 here, but lambda you can pull out, and then everything else cancels out, and you're left with lambda. So anytime you have an eigenvector, its Rayleigh quotient with A gives you the corresponding eigenvalue. So once you have the eigenvalue and eigenvector, then you can carry out deflation, like I mentioned before, by making a household reflection so that when you apply it to your eigenvector, you get E1. And then this matrix, as I described last time, will be block upper triangular. So then you can work on like the lower right block of that to find the rest of the eigenvalues and eigenvectors. Okay. And I actually once wrote a Matlab code that does something like this. That well, it required some assumptions like having real eigenvalues and so forth, but it would find an eigenvector, carry out the deflation, and then recursively, it literally use recursion to find the eigenvalue of the lower right n-1 by n-1 block, and so forth, and ultimately find all the eigenvalues. It's not the most effective method, but it uses this idea of, okay, power method to find one of them, then deflate, then find the largest eigenvalue of that one, then you deflate again, and keep going. And actually, I think it's one of the homework problems, or one of the explorations in this section. I don't recall if I assigned it. Yeah. So many problems I could have assigned you, but then you'd all be extra miserable. Now, I want to give one example of an application of a power method that literally affects all of us, or pretty much anyone who uses the internet ever. Let's suppose the matrix in question is a right stochastic matrix. So what does that mean? That every entry is a probability of a transition from state I to state J. So if you're now row I, column J, and that's what we have here. And the sum of all makes it a right stochastic matrix as opposed to like a left or a doubly stochastic matrix is sum of all the probabilities in a row is equal to 1. So each row covers all possibilities. Now, when you have a situation where all of the row sums of a matrix are the same, taking a row sums is the same as multiplying by a vector of all ones. So what you end up with is the other side of this equation would be a vector consisting of the row sums. If all of the row sums are the same, whether they're equal to 1 or not, the value of those row sums is an eigenvalue. And then E, the vector of all ones, that's an eigenvector. So with a right stochastic matrix, if all the row sums are equal to 1, then 1 is an eigenvalue of P. And this vector of all ones is the eigenvector. So that's a property of all right stochastic matrices. What we can also say is because all the row sums are 1, that means that the infinity norm is 1, because the infinity norm of a matrix is the sum of all the largest row sum. You take the absolute values of all the entries in each row and sum them up, take the largest of those sums, that's the infinity norm. So that would be 1 also. Now, what that means is that the spectral radius is less than or equal to 1. The spectral radius is the magnitude of the largest eigenvalue. So not only does not only is 1 an eigenvalue of this matrix, it's the largest eigenvalue. And I don't really remember covering this. And for any natural or reduced matrix norm, if you have ax equals lambda x, x is eigenvector and lambda is an eigenvalue, then I have the following, that ax, which is equal to absolute value of lambda times x, but that is less than or equal to the norm of A times the norm of x. So if I cancel out, now x is a non-zero vector, so I can divide by its norm. So that means that the absolute value of lambda is less than or equal to the norm of A. So any natural norm of a matrix A is greater than or equal to the magnitude of all of its eigenvalues. Therefore, the spectral radius of A is less than or equal to the norm of A. So that's how we know that because the infinity norm is 1, spectral radius, in other words, all eigenvalues must be less than or equal to 1. Now, this vector of all ones, that is the right eigenvector of P. But what about the left eigenvector? So P has a left eigenvector that also goes with the eigenvalue 1. So that's an eigenvector of the transpose. Now, what is the meaning of that vector? It turns out to be a vector with which each entry is a long-term probability of transitioning to state J. Now, to go back a little bit, in the original matrix, Pij is a probability of transition from state I to state J in one step. So if you took P squared, each entry is a probability of transitioning from I to J in 2 steps, and so on. So if you in the limit, you get the eigenvector. Each entry of the eigenvector is a probability of getting to state J ever in any number of steps. So you can try to compute this method using this eigenvector using a power method applied to the transpose. All right. Now, how this is used, it's actually used by Google. Actually, I normally don't include the text of problems in here, but I want to in this case. And I'm not assigning them. Oh, there's going to be some broken references in here, but okay. All right. So here is if you create a random stochastic matrix, and you have to make sure to normalize it so all the row sums are 1. You can go ahead and compute an eigenvector. What you would find if you try this out in Matlab is if you actually took powers of P, after a while you'd see that all the columns of the matrix that you repeated multiplication of itself end up being converging to be the same, and that column is the eigenvector you're looking for. So if you create a random stochastic matrix, okay. Oh, this is just a more specific example of that. But this illustrates the idea behind what's called PageRank, an algorithm used by Google to sort search results. And what's this LaTeX error I have somewhere? Dang it. Okay. All right. This stochastic matrix refers to a probability of navigating from page I to page J in one link. It's about just by following one link. So if you imagine indexing of a whole web or a portion of a World Wide Web, then the eigenvector, left eigenvector corresponding to the eigenvalue 1 for this matrix represents the probability of navigating to any page in any number of links. So this is used to rank search results. Now, since a lot of pages don't link to each other, there are a lot of zeros in a matrix like this in the case of indexing a World Wide Web. So what Google does is they add this term onto, like this outer product, onto the stochastic matrix to give more reliable results. And that's actually called what they refer to as personalization, and they are pretty secretive about the particulars of this. So when you're performing a Google search, Google's using the power method to find an eigenvector of an extremely large matrix. And it turned out that one of my fellow Stanford students, Sep Kamvar, had asked me questions about the power method, and my advisor, Gene Golub, also helped him. And he went on to start his own company that eventually got bought by Google, and he made hundreds of millions of dollars. So I really wish I'd been more involved in what he was doing. Dang it. So, and because Gene actually was gifted shares of Google for what he did. So, oops. Okay. All right. So we have a handle on finding one eigenvector, but how can this help us find all the eigenvectors? Well, we can start by trying to find more than one. So we have a way of getting all the eigenvalues, maybe. Use a power method, then deflation, to then work on finding the rest of them. But that doesn't work so well. It takes a lot of assumptions. It's not really a good way to go. We need something better and more efficient, and more numerically stable, because anytime you perform deflation, you're introducing more round-off error, so your smaller eigenvalues will end up being less accurate than the largest ones, which are the first ones you would find. So what we're going to do instead is use a block version of a power method, and that's called orthogonal iteration. So instead of multiplying A with a single vector, you multiply it by a matrix that has R columns. And then instead of normalizing a vector in the power method, you'd perform a thin QR factorization. So that makes all the vectors you're multiplying with not just unit vectors, but they're also orthogonal to one another. So here's the algorithm. And again, there's not much to it in terms of steps. Okay, so all we do is we come up with a matrix that has orthonormal columns. Like it could be, for instance, columns of identity. And you multiply that by A, and then you QR factorize it. And the Q part, so this vector, this matrix UK matrix that has R orthonormal columns, you feed that to A for the next step, and you keep going until these U's hopefully converge. And from a uniqueness to the thin QR factorization, that's what helps it to converge. Okay, so in most cases, if our largest eigenvalue is strictly larger than the next one, then this should converge. Just like for power method, you need lambda 1 strictly greater than lambda 2 in magnitude for it to converge. Okay. Now, from a QR factorization, this matrix RK, which is upper triangular, this comes straight from rearranging the QR factorization. But ZK is equal to this. So if I fill this in here, now I have this. This is almost like a similarity transformation, except for one thing. These are not full orthogonal matrices. They're rectangular matrices. And also, they're not the same. However, let's suppose that these U's converge. Then in the limit, we get U transpose AU is R, and that is upper triangular. And now I have this relationship. AU is equal to UR because I have this AUK minus 1 equals UKRK. But if the U's converge, then all these two are equal. So what this says is the columns of U form an invariant subspace. So they may not be eigenvectors, but you can work with them, just those R columns, to get eigenvectors. So now, suppose I look at the orthogonal complement of U. So U perp is a matrix whose columns are orthogonal to all the columns of U. Then I have a following. If I look at not just U transpose AU, but I put the columns of U and U perp together and carry this out, this is actually a similarity transformation because this matrix has orthonormal columns. Here I'm taking a transpose, which is the inverse. So then I simplify this as much as I can. Now, AU is UR, so I could fill that in here. But U perp is orthogonal to U, so that's why this part ends up being 0. And then U transpose AU is R, so I fill that in here. So in other words, what I get is a block upper triangular structure. Also, the eigenvalues of A are equal to the eigenvalues of R, which are just the diagonal entries because R is upper triangular, and the eigenvalues of whatever this matrix is down here. So, so now this, in other words, what I have are little r eigenvalues of A, that many eigenvalues. So what we get from this is if orthogonal iteration converges, the result is the largest r eigenvalues of A. So it generalizes the power method. Instead of getting just one eigenpair, I get r of them. Now, I think I'll just have enough time to make this point. I'm getting down to the end, thankfully. Let's take the extreme case where little r is equal to n. So now I'm trying to find all the eigenvalues. And let's suppose the eigenvalues are separated in magnitude. So you don't have any that are like complex conjugate pairs or like negatives of each other, anything like that. If that's the case, then orthogonal iteration will converge, almost certainly converge. Then what you have is the actual Schur decomposition, because you have U transpose AU is equal to R. If this is n by n along with A, then U is also n by n. That literally is the Schur decomposition of A. So that's what orthogonal iteration would give me in the R equals n case. So we could do that and say, oh, we're done. We have the eigenvalues. But first of all, it doesn't always work. We need these assumptions. Also, even when it does work, the convergence is very slow. So it's not really a great method. But by studying it, we can find a way to get a better method. So what I do is I define TK as follows: UK transpose A UK. Then from the algorithm for orthogonal iteration, here's what we get. So TK minus 1 is from this. They're just using a definition where I've shifted the indices down. But if I look at the algorithm, AUK minus 1 is ZK. So I fill that in here. But ZK is UKRK. That's a QR factorization. So now I'm going to lump these two orthogonal matrices together. The product of orthogonal matrices that are n by n is also an orthogonal matrix, and I'm going to call that QK. So what we have here, this is actually a QR factorization of TK minus 1. Because this is orthogonal and this is upper triangular. But now, that's TK minus 1. Now I'm going to examine TK in a similar fashion. TK is defined this way. Now I'm going to introduce UK minus 1 transpose because this is identity, because UK minus 1 is orthogonal matrix. Went to the next page. Okay. Now AUK minus 1 is ZK from the algorithm. ZK is UKRK, also from the algorithm. That's QR factorization. This is identity. And this simplifies to RKQK. So look at what we have here. TK minus 1 is QKRK. That's QR factorization. TK, the next one, is RKQK. In other words, to get TK from TK minus 1, we compute this matrix's QR factorization, and then we multiply the factors in reverse order, and that gives us this. Another way of putting it is TK, which is RKQK, but RK is QK TK transpose TK minus 1. That's the rearrangement of a QR factorization. This is a similarity transformation, so we can see that TK and TK minus 1 have the same eigenvalues. Now, if the iteration converges, then TK converges to an upper triangular matrix. And the diagonal entries are the eigenvalues of A. That is a sure decomposition. And the reason why we know that is from the earlier discussion of orthogonal iteration. This matrix, UK transpose A UK minus 1, is already known to be upper triangular. But if the UKs converge, these two matrices are the same. So to limit as k goes to infinity, then we get this, and so therefore that is a similar transformation as a sure decomposition, and the result of this is upper triangular. Okay. Now this leads to what is called the QR iteration. Another short algorithm for computing eigenvalues. Okay. So we've come up with an orthonormal matrix. You can always just choose identity. And then what you do is you take the QR factorization and multiply the factors in reverse order. That's it. That's all it takes. And what happens in that case is this will converge to some kind of upper triangular form. Okay. Now, so this is our starting point for a real algorithm for computing eigenvalues. This is still not efficient. A QR factorization takes order n cubed operations, and you're doing this every iteration. So the overall work would be at least order n to the fourth. So that's way too slow. But it will be possible to make this matrix T naught simpler so that in structure to reduce the work somewhat. Also, if A is real but has complex eigenvalues, it won't converge completely because you have distinct eigenvalues having equal magnitude, so that's a problem. But what we get is a block upper triangular form. So 1 by 1 or 2 by 2 blocks. 1 by 1 for real eigenvalues, 2 by 2 blocks for complex conjugate pairs of eigenvalues. And that's perfectly fine to converge to, because if we converge to that, then we can get the all the eigenvalues, real and complex. So in the last few minutes, I want to show you how what this looks like in Matlab. Okay, so unshare, reshare. Okay, so I'm going to make a random matrix. Let's say 6 by 6. Oh, format short is enough. Okay, and what I'm going to do is I'm going to take the QR factorization of A, and then overwrite A with the QR factors multiplied in reverse order, and then see what that matrix is. And as I do that, let's take a look at what, if I do it repeatedly, let's see what happens to the matrix. You'll see we start to get some zero entries down in the lower left. So if I keep going, we get more of them. So now the matrix is quasi upper triangular, not entirely, because we have some non-zero entries in the lower triangle here. Watch this entry right here, minus 0.0172. If I keep going, it is getting smaller, just slowly, but it is going away. Let's make it go away entirely. Okay. So now it is almost upper triangular, but we'll have this 2 by 2 block that corresponds to complex eigenvalues. If I look at the eigenvalues of A, we do in fact have these two that are complex. Here the largest, and then the second largest, and then this is the third largest. But notice if I take the absolute value of the eigenvalues, these two are fairly close to each other in absolute value. That's why this entry took a long time to go away. So when you have eigenvalues that are clustered, it takes longer to get a reduction to this quasi upper triangular form. But you can see that this QR iteration really works. It is, at least to some extent, eigenvalue revealing. But again, it's much too inefficient. So the next classes will be spent on figuring out how to obtain an efficient, practical, and reliable algorithm for getting all of the eigenvalues. It's actually my favorite algorithm of this class, and it's the algorithm is named one of the top 10 of the 20th century. Okay, so I am out of time, but If anyone has any questions, certainly they can ask. Or homework questions or anything of the sort. Oh, someone left. So, okay. Okay. Well, some of you need to unfry your brains for PDEs. So, and I need to brace myself for that too. So I will stop recording here. Anyone has questions, of course, can stick around for that.